Hi, everybody. Welcome to the Sophie seminar today. And we have lucky to have Doron Puder.
Thank you. Yeah, the first time I hope not too many people show up to my talk. And
You can kick people out if they.
Survivor. Yeah, okay, so I hope we can stay here. So this is, I'm going to talk about random matrices and algebras. I'm not assuming you know what algebras are, and I will explain them. And this is joint work with Danielle, Ernst-West, and Matan Seidel from Tel Aviv. And okay, so throughout the talk, we fix. So here K. So K here is just a finite field. So this will be probably the only common point with yesterday talk. And F is going to be a free group. So I will also remind you what free group is. And we can assume for simplicity that we only talk about F2 in this talk, which is so the group generated by X and Y. So again, first of all, we mentioned it already now. The elements of this group are just reduced words, this form. So on just reduce words in these elements. And this is again F2 just for simplicity for the sake of the talk. And what are I'm going to talk about word measures. So word measures are just different words for saying, I mean, these are random matrices generated sampled by words. So we fix for fix a word in the free groups or such a pattern of letters. And G is any finite group. It can be actually more general than that, but for now, let's talk about finite group. And W random element from the group is obtained by, it's very shorter, is W of G and H, okay, where G and H are elements from the group which are uniform, independent, and so I just take two uniformly random independent elements from the group and I plug them in my word. So I replace the letter of the word with my element and I take the product. So for example, if my word is xy to the minus 2, and my elements are G and H, I'll just get GH to the minus 2. Okay, and this is an element from the group, and this is how I sample these words. These are random elements from the group. And now this has many generalizations. I can take my group to be not compact. I can take Haar measure. I can also take the way I sample my elements. It doesn't have to be from a free group. There are other ways, natural ways to do it, but I will stick to this regime in this talk. Okay, and I will soon give a concrete example so that you can get used to this notion. I want to say a few words about. You have a question?
No.
About motivation. So there are a few motivations for studying this. One roughly is random walks on G. And I just want to mention that, I mean, this was actually the initial motivation for this study of these groups. And the question we wanted to study, it's actually still open. We didn't make any progress in this question. But I would just mention it's a nice open problem. If you take two random elements from, let's say, GL and let's say take the field of two elements, say even. Take two random elements here, and you look at any Schreier graph. So you look at the action of this group on, say, vectors of size n over the field. You can look at the graph that you generate by this action. It's an expander. But this is open, it's not known. This
N equals 2 or something, right?
no, yeah, it's known when you fix the degree and you let the field grow, then it's known. But if you fix the field and you let n grow, this is open.
So what is open setting?
If you, I mean, so I look at the Schreier graph of GL and let's say over F2. So I fix the field and I let this grow over the, and I look at the action on just on these vectors, and I take two random elements. So is this a sequence of expanders? This is not known. It's known when there are more than, let's say, there is I don't know, in this case, 16 generators, or when the number of generators grows is, I don't know, the size of the field to the cube or fourth. So it's known, there is something known, but with two generators, it's
There is something known, fixed number of generators and going to infinity.
it's known if, yeah, no, it is known if the number of generators, it's a function of the field. Yeah, so for F2, I think if I have 16 elements is known.
But then for larger fields,
You need more.
elements?
Yes, yeah, right.
So you need more elements.
I mean, I'm saying this is what is known.
The Lubotsky, Kasabov, Nikolov says that all
Right. No, I'm talking about random. I mean,
random.
right.
Good.
Yeah, no,
Yeah.
no.
Okay,
Non-construction, yeah, it's known that there are, you can pick two elements. There are pairs of elements. I think. Yeah, I'm not sure about two. No, I'm not sure about two. But anyway,
Okay.
We're saying it's clearly true, but it's not.
it's clearly true, but it's unknown, yeah. So again, what is unknown, if you pick two random elements, is this family of expanders with high
Can you
probability.
remind us what the Schreier?
Yeah, it's not, even though it's out of the, it's not the point of the talk, but I can, yeah, okay. So I just look at it's a graph where the elements are this set. Okay, perhaps we should take out zero at all. The vertices are these vectors, and you put an error. So, and you have, let's say, two generators, G and H, and you put a G error, a G edge whenever G takes one vector to another vector. This is G, and you put an edge vector whenever you have an edge. Sorry. So you just generate the graph, and then you can you ignore the directions of the edges. Okay. Anyway, this is one motivation, and as I said, we didn't make any progress here. Another motivation comes from the theory of, I could say, the topology of the free group. Yeah, you can try to separate orbits in terms of the automorphism of the free group in terms of these measures. But so here we made some progress, but it's not going to be the main point of the talk. The main point of the talk is the third motivation, which is the fact that there is this, what if you start looking at these questions, you find very I would say deep structure, or I mean deep, you find just beautiful mathematical structure when you ask these questions correctly, and it leads to natural and useful invariant support. So I will say more about this, okay?
Deep structure of what, of the free group of G.
No, just okay. Okay, that's really nice really nice results or really nice connections between these measures and properties of the of your words and yeah, this is what I mean. Like there is a lot of yeah, I think of it as a mathematical structure. Okay, so and which side of it? Okay. Okay, and so the outline, and what I'm going to do today, first I'm going to talk about some background. To be quite short, I'll talk about free groups and about word measures on Sn. So on Sn, and then talk about what we know about. I mean, I'll start with G and K, and I'll start with the elementary results. And then we'll see how full group algebras enter the game. Okay, this is the outline. And please stop me if you have any questions. We do have a long time here today. So I'll start with background. Okay, so I already mentioned. So first, I want to start with free groups. Okay, so I already mentioned that the elements are, and again, we for the sake of this talk, I'll talk about the free group and two generators. So we already know that we already mentioned that the elements of reduced words. So reduced means reduced words in y, x's, and their inverses, and reduced means that we cannot have x inverse. If we have that, we just ignore it. We delete both of them. So, and the product, you take the product of this group, you just take two words, you concatenate them, and you reduce. And what else is important? There are bases. So it's called a free group. It means that it has a basis. So a basis is in this case, for F2, it's any pair of elements. A basis is a pair of elements for F2, which generate the group freely, which means that every group can be expressed, every element can be expressed uniquely as a reduced words in these two elements. So, so we have the notion of bases, and as example, so we have the original basis that we started with, but we can also take y inverse or xy. Okay, this is also a basis. If you try to, first of all, you can express any element of the group with these two words, and there's only a single way to do it. And here's another fact. Oh, perhaps I should say that it's important later. Okay, not every only, I mean, a generic word, even generic word. I mean, if you take a random word of length 1000, is not part of a basis. So most words are not part of the basis. Another nice fact about the free groups is that if you think about subgroups, so I want to look at the subgroups of the free group, and they are what they are in one-to-one correspondence with what is called Stalling graph. Which are, you can also think of them as automata. I'll just give it, I'll give an examples for that. So I'll draw two examples. This is one example. Can you see the red? Yeah, it's a small one. Yeah, so I put a base point, x, y. Yeah, so this is an example for a subgroup. How does this correspond to a subgroup? I marked a special vertex, a base point, and the words in this subgroup are all the words that correspond to closed paths that start and end here. So for example, you can look at x, y, x inverse, y, and you can do all sorts of stuff. You can convince yourself that what I described here is in fact a subgroup. It's slightly harder to show that every subgroup can be depicted this way. These are not hard facts. There's another, I'll just show one more example. So what is this subgroup?
Even length word.
Yeah, the words of even length, right? This is all the subgroup of words.
Finite index for all subgroups or?
No, so this is one. This one is of index 2, this one is of infinite index. Actually, the way you see it is that, yeah, it's an exercise, but here all the vertices are full. You have a degree 4, you have incoming x, outgoing x, and for y the same. Here you don't, you have, like, here there's a missing edge, and here there's a missing edge, right? Here there's no incoming x. And this tells you that the group is of infinite index, even though the graph is finite.
Why?
Because I mean, basically, you can put here another thing in the middle, which is the Schreier graph of the. We are back to Schreier graphs. I mean.
Yeah, I knew I wanted you to.
Yes. Yeah, I mean, basically, you can also draw the full Schreier graph, which would look like that, and the full Schreier graph of the. And then, I mean, and this is the graph of the Schreier graph depicting the action of f on the cosets of h. And the full Schreier graph,
This is like an infinite factor.
it will have here and here infinite hanging tree. And this is, the core is when you trim all these hanging trees and you get to the, yeah. And then the number of vertices is really and in the Schreier graph, the number of vertices is the number of cosets, which is the index. Okay.
But you're not assuming H is finitely generated or something.
No.
That's
Right.
funny.
Yeah. I mean, if it's infinite generated, the graph will be infinite. Yeah. And another important fact, and this is a theorem of Newton and Schreier from about 100 years ago. I mean, 1820s. So every subgroup is free. Now, okay, what does it mean free? It means it has a basis. It means it has some generating set, such that you can every element of the subgroup can be expressed in a unique way as reduced words in the generator. This is what means to be free. And I mean, the original proof in the 1920s was a bit cumbersome. But actually, if you think about it this way, it's very easy to understand why every subgroup is free. So, I mean, I'm not going to do the entire proof, but you can convince yourself that if you choose here any spanning tree in this graph, so for example, this is a spanning tree of the graph, then and you think about the remaining edges as generators, and this will be the generating set of this subgroup, then every closed path will start here and return here. I mean, if you know exactly, if you record every time it passed through one of these edges outside the spanning tree, there is a unique way to recover the original path. So if you have a closed path and you just know every time, you record every time it passes outside the spanning tree, you can recover the original path. And this means that
On what you showed now is actually two steps. What you explained is why the fundamental group of a graph is free. This is clearly a fundamental group of a graph. That's
yes,
right.
yeah.
The spanning tree trick is like showing that the fundamental group.
Yes, right. It shows that, yeah, you're right. Yeah. And any graph, the fundamental group of any graph is free. Right. And just notice that you can find, I mean, what you see here, if you follow my argument, the free group here is actually a free group rank 3, because we have 3 edges outside spanning 3. So this is a copy of F3 inside F. Okay, so notice that the subgroups can have an arbitrary large. Arbitrary logic. I mean, it's most countable, right? But yeah.
Two of the generators are the same, right?
Sorry.
But two of the generators are the same.
Sorry.
Two of the generators are the same, right? So how rank?
No, the generators will be XX, XY, and XY inverse.
Okay.
And
Yeah.
that's three different.
X, Y,
Oh, okay. And XY.
and X, Y. Yeah, for example. Yeah. Okay. Any other questions? Okay, so this one. Yeah, this is what I wanted to say about free groups. And the second part of the background is about word measures on Sn. So why do I talk about word measures on Sn? Because this is a slightly simpler case. I actually talked about it in the seminar 9 years ago or 10 years ago. I'm sure you all remember. And I mean, it gives some of the motivation, because some of the motivation and for this work. Okay, so I want to mention briefly what we know about Sn, and perhaps I'll start with an example, but we have time. So I want to start with an example for an actual word measure. So let's fix W. Let's take the commutator word. Okay, this is. And we'll take S3. So n equals 3. So what is the, so we get a measure on S3. What is the measure? So I can tell you for every permutation, what is the probability that we get it? Okay, so we have the identity. Okay, so the game is we take 2 random permutation, we plug them here, we take the commutator, and we see what we get, right? So what is the okay? Let's start with what's the probability to get 1, 2? 0. Why? Why?
Because it's an odd term.
Yes, because this is an odd permutation. This is always an even permutation, so probability here is 0 in this case. Okay, so now we have 2. I mean, because of symmetry, actually it's always true that in this regime, in this probability space, every conjugacy, every 2 elements in the same conjugacy class get the same probability. It's not hard to show. Okay, in terms of the identity, so how many you want to count how many pairs of elements in F3 commute. This will give you the identity, and turns out that exactly half. Yeah, you have exactly 18 out of the 36. So the probability here is 1/2, and here we just split the remaining probability. So this is what you get. Just as an example. Okay, but what do we know? So how do we study these measures? We study Fourier coefficients or some statistics, and we'll focus on the defining. We'll call it the defining character, but which is just the number of fixed points. So this is the number of fixed points. And I will denote it by E, S, and W of fixed. Okay, this will be the average number of fixed points. Okay, again, if I take a random permutation, a random W permutation in Sn. Okay, and what do we know about that? So the first result I want to mention is due to, okay, this chart is almost done. Okay, so Alexander Nika in 94, he showed that for every word, expectation inside with the rational function for every large enough n. Okay, so what does it mean? It means that there is an example. If you take the commutator in Sn, so now this is now like
The
what
whole
I
wave is not very visible.
oh, sorry.
Red color is, well, I don't know who else suffers from this.
Yeah, no, you're not the only one here on the Zoom. Yeah, so what I wrote is the expected number of fixed points when I fix the word and I let n vary. So this is a sequence of numbers, right? Here's a sequence, there's a parameter n. So this is, it turns out this is 1 plus 1 over n minus 1. This is for every n at least 2. Okay, you have one data point, you can check it. That it works for n equals 3. Right, when n equals 3, you get here 1.5, and this is, you can check it. This is indeed the average number of fixed points. Okay. And he also showed that if W, you write it as a power, so now here U is a non-power, and D is a plus 1, so this D, so you write it as some non-power to some exponent, then the limit. No, I mean, it could be, I mean, W may not be a power. If W is not a power, then U equals W. Yeah, this is for any word. Yeah, so the leading coefficient, okay, it should be not the trivial word, then the limit of this expected number of fixed points as n tends to infinity is just the number of divisors, positive divisors of D. So for example, if my word is a non-power, D equals 1, you get here 1. So the limit is 1, which is what you get for a uniform random permutation. I will say okay. I'm not going to give you the proof, even though this is, there's a very simple proof for this. For this, I will give you just a clue for the proof because it's going to be important later. So I want to illustrate with the commutator. So how do I count this? How do I approach this problem? So I look at so what I want to actually count. What I actually want to count is diagrams where this is X. And I look at, so every fixed point of this word, I can imagine it as a sequence of 4 numbers where now I, J, K, and L are numbers in between 1 and n. And this describes the trajectory of the point I through the word. So now, I mean, you should think now of x and y as permutations. Take I to j, x takes I to j, and L to k, and j to k, and y takes j to k and I to L. And you just want to count all these possible diagrams. When you go over all pairs of permutations and all four tuples of indices. Okay, this is what you want to count to understand the expected number of fixed points. And what it turns out that you can, if you do the only one step that you need to understand is that you need to divide all these diagrams into finitely many cases, depending on which of the I, J, K, and L are the same or not. Okay, so case one, let's say that all distinct, and then you can just write, you have these diagrams, and now this diagram also tells you that they are distinct, but case two, as an example, is I equals L and J equals K. And they are different from each other. So I will draw it like that. Okay, and this is I equals L, this is J equals K, and so on. You continue like that, okay? All I did was I had a counting problem. I split it into several cases according to whether or not these four tuples are the same or not. Okay, that's it. And it should be clear that there are only finitely many cases. And then I'm not going to do the computation because I will later do a harder computation. You can convince yourself that each such case is a rational expression. Okay, this is a concrete enough case that each one of them is a rational expression. And you can, and this proves this result and slightly more.
What is the main term here? Which expression, which case?
Okay, good. Yeah, so I will mention it in a second. Right, the main term will give you the second result, the limit. Yeah, I don't want to erase that because you should notice something that you already saw this picture, right? In this talk. So this is, I mean, okay, you don't need what I'm going to say now for proving this, but if you want to move on and to understand deeper things about this expected value, you should notice that what I drew here are actually subgroups of the free group. Okay, so each such case corresponds to some subgroup. And okay, yeah, so I'll write an observation. So each case corresponds to some trouble. This is obvious. And if you do the exercise and show that each one of them is rational, you actually see that the contribution of every case is of order n to the 1 minus rank to the subgroup. Okay, so it turns out that the important thing here, I mean, for every such subgroup, you need to understand the rank, and then you know what is the contribution, the order of magnitude of the contribution to the to this. So, for example, so what is the? And of course, by what we said before, we need to take so the order of contribution is larger when the rank is smallest, and in fact when the rank is 1, which is here. Okay, so the cycles, only cycles give you a contribution of order 1, and it's not hard to show that the number of, and the number of cycles is exactly the number of divisors of D. That's again an exercise.
How should I think about every case is a picture and every picture is a sub.
Yeah.
But is there a way to understand how these cases correspond to subgroups?
You mean which subgroups?
What does the subgroup have to do with the specific case?
It doesn't really have to do. I mean, you can say that another word to generate the cases is just to look at the. So what kind of subgroups show up here? I mean, there's nothing really special about the case. This is a combinatorial picture, and it's not. You can actually express W in a different basis, and you will get a different set of cases and different set of subgroups. So the subgroups are not. The set of subgroups you get here is not really canonical in any real sense. But I mean, if you want to understand it, you can just think about the subgroups that first of all, they all contain the word W because, right, they all have this cycle inside, this W cycle that reads my words. So these are subgroups that contain my word W, and they can be generated from elements that, okay, you know that I think when we get to GLN, it will be, I will say it more details.
Doron, this is a computation, right? I mean, you started with random permutations, you do some elementary combinatorics to compute each of these cases, right?
Yes.
Now you're saying now you can interpret whatever the answer is in terms of the rank of these subgroups.
Yes.
Is there some like more direct connection? Like you can view these as representations of the free, right? Random representation. Like could you have done this not combinatorially, but somehow directly see that you should get this kind of behavior?
Yes, you can think about, yeah, okay, it's a good question. So you can think about a random permutation from, yeah, you have, I mean, basically what you have here is you look at this word and you have a map to, I mean, this is the free group, the subgroup, the graph corresponds to the ambient free group. And another way to think about fixed points is to take a random cover. So this is a random n cover. Or n lift. Some people call it n lift, but a random n cover of this graph. And so you have, I mean, I think we saw this picture in your talk and also in Joel Friedman's talk in the seminar.
It's a
It's
random n cover because you select a random permutation to replace
Yeah.
x and a random.
exactly, yeah, I select a random permutation to replace x, a random permutation to select y.
And that's like a random matching upstairs in the income.
Not exactly a random matching because these are, it could be self loops,
Match
but
to yourself.
yeah,
Cycles.
yeah, it's a random permutation on each side here, you know, say. And then the expected number of fixed points is actually the number of so the number of lifts. You know, this is actually a cover, this is a lift, I mean, this is the right notion. How many times you can take this, you can find this cycle here. Yeah, and here in this picture now, the image of every cycle, you can think about it, it's actually, it's a subgroup, I don't know.
But this is still a finite picture, right? I mean,
Yes.
the rank of H there is in the free group, right? In the universal cover. But you've described here what's going on in the universal cover, not in the finite object. At least. in the order.
Yeah, okay, so I don't know, so I don't have a better answer to this question.
That's why I want to think of it from up down rather than down up, right? Think of it as a random representation of the free group, and then maybe, you have some representation theoretical explanation.
Yeah, no, I'm not, I'm not sure that okay, right, so like Ramon said, I mean, this is only combinatorics. This is, I mean, you don't need this to show this, but what you don't need this to show the following thing. Is that, I mean, then you can ask yourself, okay, so we understand, we know it's a rational expression, we know we know what the leading term is. But we also know that for non-powers, you get one. What is and then you can ask, what's the order of magnitude? Of the expected value, the average number of fixed points minus one. After you subtract from one, how does it look? What does it look like? And the thing is that there are cancellation. I mean, there are many contributions of this kind, but when you move past the first the first term, the leading term, you get cancellation. For example, from the big cycle, you get these expressions, these things. So there's a lot of cancellations, and so
What cancels what? I'm kind of lost.
so I mean, if you want to let's say you want to understand the next term. So you have the rational expression. You want to understand the Taylor expansion. The Taylor. This expansion of this as a how is it called?
Power series.
Yeah, the power series. Yeah, of 1 over n. Okay, what is the coefficient of 1 over n, for example? So where do you get contributions? You get contributions from groups, subgroups, or graphs of rank 2, right? This gives you, each one of them gives you n to the minus 1 times 1. But you also get contributions, for example, from a cycle. Every cycle gives you 1 plus O of 1 over n. So you get, and this is going to be a negative contribution. So there are cancellations. So how do you approach them? So what we showed more than 10 years ago, this is the publication day, that it cancels the contributions cancel perfectly as long as W is a basis element of the subgroups. Okay, so it means, so now when I look at these expressions, so I first look at subgroups. So here I look at the subgroups of rank 1, which contain my word, and then subgroups of rank 2, which contain my word, and then subgroups of rank 3, which contain my word. And as long as my word is always primitive, is the basis element in all these subgroups, there's perfect cancellation. Meaning, so I will now, so officially I will define primitivity. So I will define the primitivity rank of. So what is this number? So this is there's a number here. So I go over all subgroups of my free group, which contain my word. But I want W to be, W is not a basis element in H. So H is also a free group, right? It has bases. And now I'm saying W is not a basis element, and I'm taking the rank of H, and I take the minimum of all possibilities. Okay, so I want to capture the first time I see that W is contained in a group, but it's not a basis element. And then the theorem is that, I mean, and what I say here, that the cancellation, there is perfect cancellation. It means that if I look at the expected number of fixed points, -1, so the leading term is captured by this number. So which is n to the 1 minus 5. So this is the first time I see subgroups of this order. Okay, I should put here some coefficient times 1. Okay, this is what I mean.
So the other coefficients are just 0.
Yes, or 0. I mean, yeah, you could, I mean, the first one is 1, but if you subtract this one, and then you get zeros, and then you get the first time you see a non-zero is here, and you can guess what is the coefficient. It's exactly the number of subgroups you see. These critical subgroups. The subgroups. The first time you see that the word is not a basis element, you just count how many times, how many subgroups, the number of critical subgroups. Okay, so, and okay, before I finish this background part, so I should just say that, I mean, this is okay, so you see, I mean, this is what I talked about at the beginning, that this is the kind of results that I'm interested in. Both because I just like them, and because it turns out that, I mean, this invariant of the word turned out to be important also in other places, in other places. So for example, it turned out that it plays a role in one related groups, and so I mean, this kind of questions and study leads you to natural invariants, and which are also useful. Okay.
What is the invariant here?
So this is the invariant. Yeah. So it's some kind of natural. I mean, some kind of invariant, which we discovered because we asked these questions about random permutations, and
The primitive element is what, how do you,
right. So if my element is okay, so I for some reason I decided not to use the word primitive because I thought, but yeah, primitive is just, I mean, it's a basis element. So W is not a primitive again is a basis is an element of a basis. So W is not primitive. If W is primitive in the ambient group, you can show it is primitive in every subgroup. So this will be infinity.
definitive?
Yeah, and if you plug it here infinity, it means that this is zero. So actually, the expected number of fixed point is exactly one. Whatever n.
So can you say something? I mean, this theorem captures cancellation.
Yes.
What kind of techniques do you use to see this cancellation between these different words? Just some keyword.
Keywords,
Yeah.
maybe some inversions. Yeah, we yeah. Yeah, I'm still looking for a better proof in a sense. Like, I think there should be a better proof, but. Okay. Any other questions about,
What do you call it, invariant? What is invariant?
I'm not sure. I mean, it's invariant out of the automorphism group. I mean, one important aspect of this is that this is actually a property of my word as an element of a group, not as the way I wrote it combinatorially in a particular basis. So this means that if I change the basis and I write it in a with different set of letters, it will be the same. So it's invariant under automorphism of the group. I mean, yeah, I'm not actually sure. I mean, people use this word all the time. I'm not. This is my interpretation. I'm not sure.
Doron, can you say again when it will be infinity? What is the property of a word for which this is infinity?
Right, so it's infinity if and only if the word is primitive. It's a basis element of the ambient group.
Okay.
Of the free group I started with. So this, yeah, I mean, yeah, the main output, the main thing that this showed was that I mean, this was one of the initial motivation.
The starting point was to try to show that a word is the uniform.
Yeah.
If and only if-
So which words? Yeah, you look at this, and which words give you back uniform distribution on the permutations?
Something you can compute.
Yeah. Okay. Just a second, but so the question is which words I plug in this word measures. Which words give me back the uniform measure? And this shows that only exactly primitive words, exactly words that are part of a basis in the original group. I mean, it's easy to show that these words have this property. They induce uniform measure, uniform distribution. But the converse is the hard part, and this shows the converse. If my word is not primitive in the ambient group, then this thing is finite because you can take H to be F. If H equals the entire group, then you get here some number. So this minimum is not infinite. It's a finite number, and then you see that the expected number of fixed points is not what you get, it deviates from what you get from uniform distribution. Okay. And you ask if there is a.
If you don't know words, can you compute this?
Yeah, so it's not officially, yeah, but you can just draw all these graphs. If you draw these graphs, there is a way to read from this. If you take a word and you write down all the graphs that you can get from merging vertices and so on, you can read.
So the size of the graph is bounded by the length of the word or something?
Yeah, but
It's an
it's exponential, yeah.
But not more than.
Yeah. Okay, in practice you can do it. I mean, for words longer than 20, Okay.
Any idea about the higher order terms?
The next terms? No, it's a good question. No, I mean, we don't know it for SN. We know more in the other groups, like in unitary groups, we know a bit more about the other terms. But here we still don't know. But it's not going to be as a simple answer as that. It should be. I mean, in the unitary groups, the other coefficients, I mean, if you continue the expansion, is given in terms of Euler characteristics of stabilizers of some. I mean, it's much more involved.
So
So
you
you
look,
get the uniform distribution just for the symmetric group or for every finite group in case it is infinite?
In case it's so infinite means it's primitive, it's part of a basis, and then it's an exercise to show you always get. It's like imagine the word x. If my word is just x, then by definition I get uniform distribution on every finite group.
Okay.
And it's the same, it's almost the same proof. I mean, you can show that all these measures, distributions are invariant under, if you change the word by an automorphism of the free group, you get the same measure. So, and all these primitive words, all the words that are part of a basis are given by an automorphism from X. So,
Nice.
okay. Okay, so, okay, so the second part, this was the background. And the second part is GLMK and elementary. Yeah. Let's see if I can do something in 5 minutes. Okay. Yeah, you know, perhaps I will say I want you to start thinking about GLN. Yeah, I mean, so what I'm going to do now is this part should be the analog of this part. Okay, so everything was, I mean, I will do it with more details, but you see everything is combinatorial and elementary. And the third part should be the analog of this part, which is the more interesting part. Yeah, so you know what, I'll just start with let me start with few more minutes, we can start thinking about GLMK. Okay, so I remind you that K is a finite field of order Q. And again, we have a measure, so we have when we fix a word, we get some distribution or relative distribution on this group, on all these matrices, and we study Fourier coefficients. And again, we start with one, right? Oh, actually, another question you didn't ask is what about other Fourier coefficients here? I should say that there's still, I mean, so actually there are many open questions, and actually there was also some recent progress, very nice progress about general Fourier coefficients of this. So this is still live, and this is still very much alive. This.
You replace fixed by something else. That's
if I replace fixed by some other Fourier coefficients, other statistics of the word, what do you get? And there's a beautiful recent result by Yun Cassidy, who shows that. Okay, I don't want to. It will be hard to explain what it is, but my point is that there are still many open questions and results in this for random permutation. So now GLNK, and I want to focus on the average number. Again, I will call it again fixed, but now it will mean something else. This is the number of vectors in FQ to the n fixed by the fixed by an element of by some matrix. Okay, and I will denote by.
Why is it different?
No, I use the same, it's fixed, but it gives it a different word. I mean, now it's
not the dimension.
Yeah, no, not the dimension, that's number of vectors. And so we'll denote by En W now, of fixed, which is, I don't want to write GLN, okay, all the time. Okay, this is the expected number, the average number of fixed points over W1 to matrix in K. And the warm up. So what is?
Is it obvious what it is for just a random element?
Yeah, that's exactly what I want to say. So now I took W to be X. Okay, so now I just take a uniformly random matrix and I ask how many fixed points it has on this space of vectors.
It's a zero.
It fixes 0, right? So and then on purpose, I'm not going to, because what we do afterwards, I don't want to take it. I want to keep 0 in. Okay, this is more natural for the other part of the work. Okay, so it always fixes with 0. And what about the other ones? The other ones, I mean, it's one orbit. It's a transitive action, and if you have a transitive action, you take a random element. It's always every orbit gives you 1 to the. Okay, I'm saying this is 2. Yeah, you could take just think about it. Take any non-zero vector. It goes to any other non-zero vector with equal probability. So the probability it is a fixed point is 1 over the size of the orbit. And you just multiply it by the number of orbit, the size of the orbit to get the expectation. So you get 1 for every orbit. This is 2. And what I will show you after the break is with this is the elementary part. That for every word is expected number of fixed points. Fixed vectors coincides with some rational function due to the end for every dimension of this. And so we'll start with this. This will be the elementary part, and then we'll give interpretation in terms of a bit more sophisticated interpretation.
So can this be done combinatorially also?
Yeah, this will be done combinatorially, yeah. So, yeah, you need to understand what is the analog of these cases. I mean, what's the right thing to do here? But, yeah. Okay, so let's take a break of how much time? 2 minutes. Yeah, 10 minutes. So let's be honest. Good to the end. I mean, it's wonderful, good to the end, doesn't matter.
What side of the set you act on?
No, it's good to the end.
Why did we have problems with exponentiation? We had problems because it was a rational function 1 for n, but it only sets in as 2 to the n, something.
There's a collision?
No, I think there's, I mean, the problem is that the values you get to are.
It's my fault.
The problem is that
Large
only when
space.
n is larger than the word length, which is q to the. It's when n is larger than the word length, not
It's not
q
the
to
most
the n.
exciting, like, it's a good result, but
That was the problem.
mostly it uses old ideas to
Yes,
resolve some open,
yes.
previous open question of shy. And
So you actually need the parameter of the rational function to be
it's
exponential
the
in
same
one.
groups.
Yeah.
I see.
So I didn't really care.
Is that
Unless somebody
related
else
to the-
published.
Oh, yeah, you told me about that, right? Not me. Is that related to the rankings?
Go on.
So that's another thing that I
Oh.
should, but that I didn't have the result. I
If
suspect.
you look at the action of the symmetric group on pairs, will it be a rational function in n choose 2?
No, it will be a rational function in n.
Stuff.
No, you still need n.
Also.
It will always be n, or I mean, it could be n minus one.
They also.
We're not sure actually, but what's the right thing, but it's n.
So it not necessarily depends on the size of the set you act on.
Yes,
The rational in
but the
some-
leading term, but we suspect that the leading term, if you take, okay, you have for example, the action on pairs, I mean, it contains the action on singletons.
Yeah,
But if you subtract the action on singletons,
yeah.
we think
It shows.
I mean, it should be the same as, you should get the same result, but with here n squared, or, you see, I mean, this is where the n squared should get into the picture. You should get,
I see. If you look at the irreducible,
yes, exactly. Look at the irreducible representation, which is dimension n squared. You should get here n squared to the 1 minus pi.
Yesterday,
okay.
Not n to the 1. But the rationality is within n.
And this will happen to any finite group?
So it's reasonable not just finish writing it.
I see.
You need to have some stable representation theory. So you need to have, you see, I mean, Sn is a family of representations, and you have these are only the action on singletons, the action of pairs. These are special representations that they really, it's like you can define it once for a whole family of groups in a very strong way, and
Yeah.
so it should be true.
We already had these results.
Like in Ramon's lecture, you need it to be stable representation.
Yes.
It's fine.
Okay.
That guy's some interesting interpretation of the sixes.
This is a combinatorial interpretation. How did we get to something infinite about the free?
No other,
Why do you say infinite?
The free group is an infinite block.
Yeah.
Not right down to zero.
Because all these core graphs are finite graphs, right? So
In fairness.
the subgroups are defined with finite graphs.
This year.
Yes.
This is not just how you're reinterpreting the finite
Yeah.
graph just in terms of rank of the subgroup. It's a finite.
That's how.
That was why I asked him whether there's some.
Yeah, last time I had a paper.
But also when
It's
you
a way
ask
of working
about
directly with you.
If this one, try this
uniformity,
on the other.
you're asking about
So far.
letting in a random word from some finite group, not from.
Finite,
No, the word is fixed.
the word is fixed throughout.
No, there's a word, and then you plug in the G and H or X and Y.
Yes.
I just don't think.
Where are they coming from?
From a finite.
From a finite
Finite.
domain,
It's too, it's too simple.
yeah. Also here,
It's too
it's
easy to
in
write.
case of
It's
finite
like,
field.
this just
Yes.
combines. Paper X, paper Y, and like.
And you said also that you can think of some hard measure over a.
Yeah, so if you have a compact group,
Paper is totally unnecessary.
you can also define for infinite group, you can take some
You have a
solution.
measure.
Yeah, but there is no natural, these things work out nicely, which is, these nice theorems. Only when you take very natural measures, and I haven't seen yet a natural measure on random, arbitrary infinite group. But if your group is compact and you have How measure, which is very natural, then things work out. This should be measured and work out. There is, behind the scenes, there's representation theory. Representation theory works nicely with how measure, doesn't work nicely with random walk measures or something else you can
They
find.
redid the whole thing. So I think it might have been a thing.
But the story was like, you wanted, people wanted to first know specific words, do they give the uniform distribution or
Yeah,
not?
I emailed them.
And then.
Yeah, which words give you the uniform distribution? Are there words
I
that?
admitted that.
And this was your theory?
Yes.
Put that in an email.
Right, so this geometry,
Yeah.
there are n by n matrices within. But you're really viewing them as their actual
I think.
FQ to the n, right? So you're really viewing it as Q to the n by Q to the
Like I
n.
should have written
definition.
it, we should have posted it as in, it's like the results are nice. It's just
Yeah.
right now.
Permutation,
Yes.
they are permutation matrices
Yes.
that dimension q to the n, right? When you
Right.
view them as this action.
Okay.
Yes.
Not very
Is the fact that they originally come from n by n matrices, is there anything left of the linear algebra? In this? For example,
Yeah.
the spectrum of these objects have very large multiplicities.
And mostly.
If you view this q to the n by q to the n matrices.
No, because it's not, there's not, no, there won't be any, but, no, there won't be a true. If you look at the K graph, it will be, this is, the general K graph, it will be,
Somehow I'm struggling with the fact that these are very large dimensional matrices, but they are right? So, you know, is the fact that these are really n by n rather than q to the n by q to the n objects, like, does that have any reflection? It should cause some kind of degeneracy, maybe not. I mean,
Stable, it's like. Populations stable. We're looking at these methods that.
yeah, I mean, you have to get Q to the N, which is also the side of, yeah,
Don't.
no, I'm not sure.
Sure, yeah. Distribution. Distribution. Just like individually.
Yeah.
So we're trying.
Yeah.
For example, you could try to do the same thing
Yeah.
that he was saying, you could look at the dimension of the space with
Right, we just take a.
fixed, rather than look at fixed points, you could look at subspaces that are
Right.
fixed by.
Yeah,
Then what would happen? I mean, that's much closer to viewing it in the end.
Even take that.
Yes.
You remember that they should substitute.
Yeah, so, right, that gives you a different quantity, right? Does that mean?
yeah, somehow this is what,
I don't know.
I mean, in a sense, the fact that we have a theorem eventually, and I still like that, hints that this is the right way to, this is where you see the, you get an elegant result at the end, so it probably means that this is the right choice for the, to look at the expectation of, I mean, I'm not talking about application, I'm talking about,
Oh, but if you took the expected dimension of the.
yeah, it would be different.
Invariant subspace.
Yeah.
Where-
Didn't know to do.
Yeah, I mean,
Would you not get rational functions?
I don't
You
think
know?
I'll get rational functions. Yeah, I don't see how to. Yeah, because I mean, part of the story, I mean, you get rational functions because you can compute it, for example, in the permutations, and everything is local, you can just draw local pictures and get the global distribution or global expression.
What do you mean by local and global?
I mean, here I just, you see, I mean, I just, to count fixed points, I just need to look at 4 tuples, like, I have, n is very large, and I just look at 4 numbers and look how many times I see this, some small pattern in my, in the big permutation. I don't need, and for dimension, I need to look at the entire picture.
That is similar to LPC codes, like in the sense.
They're useful.
This is similar, I'm remarking to read that it's similar to LPC codes, right? Like you check a single check, it's like touches only a few parts.
Why would subspace not be local? Because you need to simultaneously keep track of the entire subspace.
Yeah, so here, for example, yeah, I need to know, how do I know how many, I want to know how many times I see. I know, that everything together is, that the entire space is a fixed point, I need to know something, I mean, when is the entire space a fixed point? Only when my element is the identity matrix, and then. And this means I need to know, I need to get to know the entire element, not just small piece of it. I mean, everything here works because I can just look at small pieces of the element. Like for the permutation, I didn't know, to count the fixed point, I don't know what the structure of the whole permutation is, just I look at small patterns and I count how many times they appear there. Okay, so let's move on. Okay, so before the break, I told you about this proposition. Right now we are in GLNK. Fix the word, you take a W random matrix in GLNK. I want to know how many times, what is the expected number of vectors that are fixed. So, okay, perhaps before we, so I want to give some examples, so you can have, before I give the proof of this proposition. So let's take W.
Well, what happens?
Yeah. Yeah, I have X cubed here. I can X cubed. Good enough? Yeah, I mean, I can think about that. Five is not hard, but it's a computation. It's a small computation. I'll tell you later. But okay, if I just take word X, just X. Okay, I already said that it doesn't matter what Q is. We get that this is always 2. Now, if I take X squared,
What is the field? What is
Q is the size of the field. Yeah. Now, if X is if I take X cubed, then it turns out to be, then you get 2 possible answers, 4 or 8. And this is only for n at least 3. And I get 4 when Q is 0 or 2 or 3. And 8 if Q is 1 or 3. And okay, the commutator, the word we're going to work with as an example all the time. Here again, I can write one expression for every Q, but this isn't really only a coincidence. It's not, it shouldn't make more than, there's nothing more than, I don't know. It's only a coincidence. So I write it like that. There's 2 plus, and then there's Q to the n minus 1, Q to the n minus Q. Q minus 1 squared to the n minus minus 1 cubed. For every n at least 2. Now notice I tell you that this is a rational expression in Q to the n, but there's also Q here, but you should think of Q as a constant. So I fix Q. So here Q is actually a number, and it really is rational in Q to the n. And one more example, let's take x squared y cubed, and I computed it for Q equals 2 and for Q equals 3. I don't have a net, so for 2, this is 2 plus 2 over 2 to the n minus 2. And for 3, it's 2 plus 4 over 3 to the n minus 3. Okay, so these are the kind of expressions that we get. And this is again for this 3, I think. Okay, so how do we prove that? So we'll prove by example. So I will take the word, again, the commutator, like we did, like we had before, but now, yeah, but you will see that there's nothing special about the commutator. You can do the same computation for any word. So here, so before we had, so now what do we need? We actually need to count. We have to some normalization. So we have, now we have 4 vectors. We call them V1, V0, V1, V2, V3, and then we end up together again in V0.
Stupid question. If I sort of formally put Q going to 1 or something, would I recover the SN versions?
I mean, I think you need to look not at this. I mean, first of all, you don't need to look at this. You need to look at the action on the projective space, projective line. Sorry, projection space. And then, yeah, I'm not sure. I mean, I think for the commutator, you do get it. I don't think you get it for a general word, but I'm not sure. I mean, there is something there, but yeah, it's part of the, yeah, like you can think of symmetric group as a field of order of matrices over a field of order one, yeah. There, you see some patterns of this, but okay, so here we want to understand the number of fixed vectors. So again, I look at the entire trajectory of the vector. So now I have in this game I have 4 vectors in my field k to the n, and I have these again x. Okay, now let's put here a, b, A inverse B equals, now A and B are these random matrices. Okay, I want to count those. All the possibilities for this, and here, of course, I mean, this diagram tells me that A takes, if I multiply A by V naught, I get V1. If I multiply B by V1, I get V2, and so on. This is what it means. So I want to count these. So what is the right way to do it? Any ideas?
Check who's linearly dependent on who.
Yes. Right, but actually you need more than that. Not just which one is linearly independent with which, on whom, but what are precisely the linear dependencies. Okay, so this is the right way to do it. So yeah, so the idea is to group together all solutions which satisfy precise same linear dependencies.
The one idea is to get a similar combinatorial picture before, but instead of like the stalling graphs getting something else, and that's the characterization, like that's the, I don't know, the box.
Yeah, I mean, this will be, yes, yeah. The idea is to repeat, we want to repeat this, but now it's in instead of an action on sets, we have a linear sets a linear action on the spaces, yeah. So the linear depends, so we have 4 vectors, in other words, in every solution, I have just 4 vectors. I can ask what are precisely the linear equations they satisfy. And this is just a linear equation on 4 elements in K to the n. So it's a subspace of K to the 4. Okay, so this is just I will do it by delta. Okay, so it's some subspace of K to the 4. And of the precise linear equations that they satisfy. And now I can write. So let me write, so the expected number of fixed points. So up to normalization, because I take random elements. I take 2 random permutations, so this is my normalization. And okay, by definition, this is, so I'm just repeating the definition. I go over all possible matrices, and I want to count the number of fixed points of the commutator. Okay, this is just the definition. So this is yeah, now I will change the order of summation, and then I will go by, I will check. So first I go over all possible vectors, and then I count the number of A and B such that, so given a set of vectors, I want A and B such that they satisfy these constraints. So I want A V naught to be V1, A V3 to be V2, B V1 to be V2, and B V naught to be V3. Right, so this is what I want to count. And what I told you here is that I'm now going to regroup everything according to this delta. So I'm going to have another sum here. And here I want to, I will do it by saying that, okay, the linear coefficients, the linear constraints, sorry, the linear equation they satisfy is exactly delta. Okay, so I'm just regrouping my 4 tuples. And the point is that, so first of all, now this is the yellow sum is finite. And what I'm going to show you is that I'm going to convince you that this is
Finite, you mean independent of n?
Yes, it's independent of n, right? It's a finite sum independent of n. It depends on the word, but I fix my word for a given word, this is finite, it's a finite number of possible subspaces.
Okay, like it-
Yeah, it depends on K on the word, but it's independent of N, and it's fine. And I'm going to show you that each one of these, this is rational in Q to the N. And this will, if I show you this will prove, I mean, okay, sorry. I mean, this together with this, I mean, I need this coefficient. Together with this will be rational in Q to the N, and then you get, you know what, let me write it properly. So you have here the sum. So this is that.
Doron?
Yeah.
I may be taking you back or to the side, but why is it important to express it as a rational function? Like what?
Because it's the first, I mean, okay, it's a fair question, but it is just the first step.
So you are still motivated by all the applications, but some.
I'm motivated by all the applications. Yeah, this is like the first step. And okay, now we have a new reason to care about rational expressions, right? You can prove expansion with Ramon's new method and using rational expression, but this was certainly not our motivation because done before. But yeah, and by the way, we don't yet know how to get. I mean, so far it's not clear that this method it can work, right? Otherwise, the open question from the beginning wouldn't have been opened about Rationality.
The problem here is in this for all n much greater than one. Right? This is not rational for, for all n, right? It's only for n large enough. And
Yeah.
in this situation, it has to be too large.
That's bad for your application.
Exactly. So this is true in this case when n is larger than the word length, right? That means that it's only rational and exponential. It's a function that's rational and exponentially small interval in the word length. That's really bad for us. Whereas in the symmetric group, it's on a polynomially small interval in the word.
But you believe this can be removed? It's very large n? Asking both of you, essentially.
I know nothing, and Doron told me earlier he thinks no.
I don't, I mean, yeah, I don't see how to move. Okay, so let's. I want to convince you that, and also say, yeah.
Question, what does it mean delta v is equal to delta?
So I fix. So for every such a trajectory of my fixed vector, so v naught is my fixed vector. And I know it's a fixed vector because I wrote it v naught. But there are some other vectors that goes by on the way when I multiply it by the letters of my word. And so for each such four type of vectors, I define delta of the vectors to be the precise linear, the precise equations that satisfy all the possible.
All alpha
All
0, alpha
equations.
1, alpha 2, alpha 3.
It's equal to
such that-
zero maybe?
No, this is my definition. I mean, I didn't write it, but I mean, I mean that delta v1, v naught up to v3, you can think about it as the set of all alpha naught, alpha 1. Such that, yeah. So this is the subspace, precisely all the possible equations that are zero, and then I group them by this equation. So then this says that for these particular vectors, I get the same thing that I'm summing over, same subspace that I'm summing over. So now we'll do this. Yeah, okay, I don't have chosen a wider part of the board for that, but I want to do some examples. And I mean, this will already be the proof. So I want to know what I'm going to go over delta and the number of. Yeah, this is not good. Okay, so I just took this this formula and I divided it into, so first, I mean, for every given delta, I want to count how many vectors these not up to V3 satisfy precisely these equations. And then for each one of them, I'm claiming that these probabilities that A and B satisfy these constraints divided by this is going to be also independent of V0, V1, V2, and V3, and only depending on delta. So let's first take this example. Okay, delta is k to the fourth. Delta is the entire subspace.
The V's are 0.
Yeah, all the V's are 0, right? They satisfy all, including, for example, alpha naught times V1 equals 0, right? I mean, 1 times V1 is 0 in particular. So they're all 0. So what is the number of vectors?
1.
1, right? They all must be 0 here. And what is this number?
1 as well.
Yeah, 1, because every matrix takes the vector. I mean, here, that's how we should say that. Here, this means that V naught, V1, V3 are all 0. So every matrix takes 0 to 0, right? So the probability here is 1. The probability is 1. The total contribution of this case is 1. And this is not surprising. This is actually the case of zeros. We know that 0 is a fixed point of everything, and it also gives us 1, contributes 1 to the expected number of fixed points. On the other extreme, we have delta is 0. So this means,
Linearly.
yeah, so the 4 vectors don't satisfy any constraint. So they are linearly independent. So how many 4 tuples do we have? So, okay, we need just how many 4 tuples of linearly independent vectors in k to the n? So the first one, it must not be 0.
Then minus 1.
The second one is, it must not be a copy, product, a power, yeah, a multiple of the first one and so on. Okay, what about this? So here, remember, A needs to take V0 to V1 and V3 to V2. So there are 2 independent vectors. It needs to be mapped to 2 other independent vectors. I can now just imagine I take V0 and V3 as the first 2 vectors in some basis. So I can express my matrix, other matrix in this basis, and then this just tell me that I want to know what are the first 2 columns of my random matrix, and they should be precise. So the first 2 columns of a random matrix have a precise value with probability 1 over. Yeah, the same thing here. Okay, and I have 2 more. Okay, these are the easy examples. Let's take 2 more examples. Now let's say I take the span over K of V3 minus 2V0. Okay. Yeah, and we assume that I mean K is now with this of size is not even. I don't want Q to be 0. Okay, you can think of Q as Q equals. So I mean now delta, I'm saying, well, let's check this case. Delta is now this case. So the only linear combination I have 4 vectors, the only linear independent.
Delta is 1 dimension and it's sort of
I think you meant 1, 0, 0, minus 2 or something, right? Like
Yeah.
the span of 1, 0, 0, minus 2,
Okay,
right? Like
okay. I mean, yes, I see what you mean. Yeah, I like to think more like that, but yeah, you can think about 1.
Or the other way, I don't know, minus 2.
Yeah. Okay, yeah, I mean that, but I want to write it. I mean, it's really more convenient to write it.
actually.
Okay, so what do we get here? Okay, I mean, I'll do it short. I mean, okay, we have 3 independent vectors, so okay, what about the number of A's? So let's see. Now A, what does A do? It takes, remind you, A takes V0 to V0 and V3 to V2. how many A's satisfy this constraint now?
It's not clear if it's compatible, it's not.
Zero, right? Yeah.
Wait, it depends whether V1 and V2 are.
No, but we know they're
We know they're
independent.
linearly
V naught and V3 are now linearly dependent, but these two are independent. This is impossible. So we get here 0. Okay, and here we get something, it doesn't matter. This gives us 0. So how do we fix that? I mean, you see from here that whatever any linear dependence we had between V naught and V3, we also need to have it between V1 and V2. So let's take now the span. So I'm going to write it in edge. So
I'll just say it's very similar to the Stalling foldings in the sense that once you say that these two vertices are the same, you maybe need to collapse it and say that these two vertices are the same in the S-end case, right?
yes, if I have two vertices in the beginning of an X edge, which are the same, they also the endpoint. Yeah, I didn't start it there, but yeah, you're right. So now we'll take V3 minus 2 V naught, and also to make this work, V2 minus 2 V1. Okay, and you can also express it like that. Okay, and then it doesn't really matter what we get, but we get something positive and rational. Okay, I mean that's the point. I mean the point is that this was my point for this example. You get something rational, and it's rational. It's not hard to show. And the final example I want to give is what is span K? If delta is this one, it tells you that I mean, okay. So again, I wrote it in a way that's perhaps not as clear, but what does it mean? It means that I want all of them to be the same. So basically, it's like the span of 1 minus 1. Anyway, okay, it's actually the span of all the things, all the 4 tuples which are of sum 0. I want the sum of all these to be 0, then it works. Okay, this is a subspace of 4 tuples which sum up to 0. And here we get just, I mean, if I know V naught, it determines all the other ones, so it's Q1 minus 1. And here we can, I mean, I have just one vector. A needs to map some particular vector to a particular vector, and B needs to map the same vector to itself. And this is the, so you take the multiple of this, you get the rational expression. So, I mean, this ends the proof of the proposition, right? Because, I mean, I hope I convince you that it's indeed a finite sum, and for each one of them, it could be 0, but anyway, for each concrete delta, I get the rational expression.
To contribute the other one, right? I mean, you have 2 plus something, who contributes the other one.
Oh, this one. This contributes the 1. You see, you have here overall Q to the, I mean, the degree here is 4, but you also have degree 4 here. Take the product. So, yeah, so that, I mean, you see that you always get these 2 here, at least 2 in the beginning, and the 2 comes from these 2 cases, where everything is 0 or where everything is independent.
What determines these constraints, like for all n greater or equal to 3 or 4?
That you need to have enough, I mean, in some of the cases you can't have, they cannot be independent if n is too small. You cannot, if n is 3, okay, if n is 3, you cannot have 4 independent vectors, right? But it doesn't matter, I mean, you get 0, the problem is here, this cannot be 0. I mean, if here n is not small enough, if n is 1, here you get 0, right? Just, yeah, just you don't get the right, I mean, you can't like n equals 1 in this expression and get the right answer. It doesn't work.
Somehow these calculations are not really what you're interested in, because you said that no matter what it turns out to be, the fact that it's local gives you what you want.
No, I mean, no. The fact that it's local, it allows me to get this rational expression. You see, I mean, I didn't. All I need to know about A and B, I should just explain what local means. I mean, I only needed in all each such cases just to know what A and B did in two vectors, 2 multiple vectors. I don't need to know the entire nature of A and B.
In other words, if you have a word of length 7, there's going to be some 7 vectors, and you're gonna need to know what happens to them, and as n goes to infinity, 7 stays fixed.
Yes,
So it's gonna be always this local in the sense, and
yeah, yeah. If I ask the question, the correct question, which is in this case, the expected number of fixed points and not, for example, the dimension of the space of the fixed points, which is not a local thing.
sure.
I mean, the correct answer for this to work, I mean, not the correct question for this. This is the correct question if you want such arguments to work.
But, so are you really interested in the fact that the function is rational, or you're interested in? the
No,
fact that
I'm
it's a
interested,
local-
no, I want to understand more. I want to understand that, I want to get, my goal is to get nice theorems like the one about SN. I mean, I want to see this connection between measures on probability distributions and invariants of words that are to find the structure like we had in the symmetric group. But I need to start somewhere. I mean, if I just have a distribution, what do I do with it? I mean, I need to find some. Once I have rational expressions, now I have like concrete numbers I can ask about. For example, here I get a rational expression. I can again expand it. I can expand the rational expression and look at the power sum and look at the coefficients. These coefficients are now numbers that are related to my word, and I can try to understand where they come from. What properties, algebraic properties of the word they come from. Okay, so but the what do you say, so I just want, before we go on to the third part of the talk, to point out the so an important corollary, the upshots. Yeah, that's the word I was looking for. The upshot of this computation, except for that you got it's rational, is that you see that we have this, what we discovered here in this example is that we have to have so delta, or the contribution of this delta in k to the 4 is non-zero if and only if it doesn't have, we don't have this. So how do we avoid this? You want exactly that whenever you have, if, write it like that, if delta, for every delta in k to the 4, for any possible equation, delta is in delta, small delta is in big delta, if and only if delta times x is in delta. And what do I mean by that? So here this means that if my delta, this only happens if delta, now I have a general word. Now let's say I have delta which is supported on x edges. And if delta,
For general word, it's still 4, it's not 4, right? For the general word, it's not k to the 4.
right, yeah, correct. Like right here, the length of. Yeah, that's the length of the word. So if delta is supported on the beginning of x edges, then I can move it. Then also after I move it by this x edge, so I get this thing. And this is delta times x. This is delta. If delta is in my subspace, delta times x should also be in my subspace. Okay. This is what we got.
Delta times x is not defined for every delta. Well, that's
Right. Yes. Yeah, if delta is supported on the beginning point. Okay. So this leads me to the third part of the talk, which is Figure algebras. Okay, so let's start with what is the figure algebra. So first of all, I'm going to I just want to introduce. So this is KF. I'm going to call it this early A. I'm not using it a lot in the remaining 20 minutes. So what is it? First of all, the figure algebra over K. This is just finite linear sums, finite linear combinations over K of elements of my F. Okay, so this is just okay, and alpha U is a coefficient for my field, and it has finite supports.
It's the same K from the GLM K.
Yes, it's the same field, yeah. The same K. So finite support, I mean, all of the alpha U are zeros except for finitely many. And this is a ring or an algebra over K. I mean, the addition is obvious. Multiplications, you multiply the elements of the free group, right? And then you get, for every two such expressions, just multiply pairwise, element by element. Okay, so this is a full group algebra. And an important thing is to know what is, and I'm going to okay, and I okay, a subset. So I said I want to use A is a right ideal. Okay, it's the same notion of right ideal, of one-sided ideal from every ring. I will remind you what it means. If first of all, if I is a linear subspace, it's a linear subspace. Okay, and it is invariant. It is closed under multiplication from the right by arbitrary elements of A. So for every I in I, let's say G in I, and for every element of the algebra, so G A is also in I. So I can take an element of my ideal, multiply it from the right by an arbitrary element, and I still remain inside the ideal. Okay, and we'll denote it by so we write it like a subgroup. Okay, this will be the annotation for us today. Okay, what is this? And it turns out, okay, so every equation we had from before on V naught to V1 up to VW minus 1, or let's say up to VW, doesn't matter. I mean, I can add another one, which is the final vector, which is the same as V naught. And every equation is actually can be it give me an element of the free group algebra. So why? Because I mean I can think about my word. Let's do the same. Let's go again to the commutator. So I start here with the element 1. Then I had the element x of my free group. Then I get the element xy. Then this is xy. So xy x inverse. This is y x inverse. Y inverse. Okay, the commutator. And now if I have an equation, right? For example, we talked before about if I put here, what was it? -2 and 1. right? I had this equation, so I think about it as minus, so minus 2 V naught plus V3. It gives rise to the element in the free group algebra, which is minus 2 plus xy, x minus 1.
Answer.
No, yeah. And what is what is the condition? This condition. So we have a set, now we have, so every delta, we can think about it. I mean, what I'm doing now, perhaps I should motivate it a bit. I mean, why are we talking about free group algebras? They are, I mean, I didn't expect them to be there when we started thinking about this problem, but we want to give some deeper interpretation of these rational expressions, the rational expressions we get at the end. Right, we have all these contributions, but can we make sense of them? Can we get something about, do we know what? Okay, I mean, so you can just take this combinatorial thing and you can work, it's a bit technical, but you can find also the leading coefficient, that the analog of, to know that you always get 2, the limit is 2 for non-powers, or to know what the limit is in general, but what is if you want to study more refined statistics, like what is the leading term after we subtract 2 and so on. So we want to understand more, we want to understand something deeper, and also to get to some kind of result like we had in the symmetric group. And what I'm explaining now shows why free group algebras are the natural thing that comes up. Okay, so I want to convince you that what we had before, this combinatorial thing actually leads to free group algebras. So the condition, so the right way to do it is to look at this and to try to understand what word this comes from. And the answer is free group algebras. Okay, so what is this? This reminds us of an ideal, because we had an element here. It only happens on the path of my word. It doesn't happen on the entire free group. It only happens on this particular element. But for these particular elements, we see that we have some element in the free group algebra, and when we multiply by x, which is what we can do if it's an ideal, we remain inside delta. Okay, so I try to argue like that this means that the equations delta are or belongs to some ideal. Yeah, I'll be more precise.
In some sense, you try to associate with each row of the right-hand side computation an ideal of the free group algebra. Like here in this picture.
Yes.
For each row, I'm going to find an ideal and I'm going to say, okay, great. Like now.
Yes, now we have something to work with. Yeah, exactly. Yeah. And yeah, perhaps you know what, I will write it like that. I write perhaps. So this is the beginning point of that is the following crucial observation. That any valid, there is a one-to-one correspondence between all these valid set of equations and right ideals. In the free group algebras, which satisfy these things. So first of all, there's something obvious they need to satisfy. I mean, I count fixed points. So in particular, this vector and these vectors are the same. So what does it mean? If I look at this equation, it means that this and this are the same. So it means that my
W minus 1 is.
Yeah, exactly. So my ideal must contain W minus 1. I mean, this is W. Okay, this is W, this is 1. So it must contain W equals 1, or it must contain W minus 1. And the second thing is that, okay, I started only with, again, I don't look at ideals that are somewhere, anywhere in the free group algebra. They must be defined somehow by elements of this path of W. So they are, I would write that the I generated on the path from 1 to W. Okay, it means that there is a generating set for the ideal that lies on, that is supported on this path. Right, okay. Okay, so now what have we accomplished? I mean, there's still more to say about it. I mean, there are some details to check why this is a one-to-one correspondence, but it's not hard. So we have accomplished that we can express now the sum that we had here before, every line in this table as related to some ideal. And you know what, perhaps I should, let me write. Don't have much time, but I think it's worthwhile to write now the ideals very quick. So let me write down the ideal we get in each case. I'm going to erase this and okay. So what is the ideal here? I mean, you just so the way to get the ideal is to look at these elements, now the equations as elements of the free group algebra, and see what ideal they generate. So here the elements are you see v naught equals 0 means that we actually get
With the all A, no?
yeah, it's all of A, right? Because it contains the element 1, for example, I mean, just the equation that is supported on 1, which is the identity element in the free group algebra. So you get everything. Here, 0. So all, I mean, 0, but it's only up to here. Actually, it must also be, it does contain W minus 1. So this is the ideal generated by W minus 1. This is the only thing that, okay, so this is W minus 1A. This one, okay, I can just take each one of these is a generator, and we already said what it was. It was xy x minus 1 minus 2. It's this ideal, and here, okay, we already mentioned these are the equations that are. This is the ideal that, for example, you want this to be the same as this, but okay, I'll just write down the answer. This is
1 minus x, 1 minus xy, and 1 minus.
yeah, but it's actually what you get here is the augmentation ideal. This is the ideal of all the elements such that the sum is 0. Okay, so we have these ideals, and yeah, I just want to state the results we have about the ideal. Okay, so this is we made some progress, but okay, still, what do we know? Can we say something intelligent about the order of contribution of every ideal? So now we know that the expected number of fixed points is given by a sum over some ideals. Do we know something about the order of contribution? Let alone the leading term. So in the symmetric group, the order of contribution was related to the rank of the subgroup. But now we have ideals. Do we have a rank of an ideal?
Number of generating set? No, like minimum number.
Yeah, so it's actually even better than that. So this is a fact that I didn't know before I started working on this project. But there is actually a Nielsen-Schreier theorem for free group algebra. So it turns out that there is a classical theorem by Paul Cohen and Jacques Louis, 60s. Said that every right ideal, it's a bit more general than that, but every right ideal is actually also a free object. So what is the right free object? I mean, first we had that the subgroup is a free group. Now, this is not what is it free as, but every ideal is also an A module, and I will explain shortly what it is. It's a free A module. And with a well-defined rank. Okay, so this means
Generation as an A module and not generation as an
yeah.
ID.
So I'll write explicitly what it means, namely, given right ideal, okay, there is again a basis S such that I is okay. Let's assume. I mean, let's assume that this is fine. It doesn't have to be finite, but let's assume it's S1 A. This means that every element in my basis, there is a unique way to write it as a product of S1 times an element of the algebra, plus S2 times an element of the algebra, and so on. And I'll give, we're out short of time. So I'll give an example, one example. IF, this is the ideal, this is the augmentation ideal where everything sums up to 0. It turns out this is a module of rank 2. You can write uniquely every element as a product of x minus 1 times something plus y minus 1 times something. Okay, and you can, as an exercise, you can write. I mean, write x, y, the commutator of minus 1 as in such a way. Okay, this is an exercise. Okay, so now we know what to expect, right? Now we have the full, we have a full way to generalize what we have for commutations. Now we know exactly what to expect, right? We have these ideals, and now, so now I'll just write the result. I should say we don't have the full result yet in this case, but let's write, so here are the theorems. And this is by Danielle, Matan, and myself.
Danielle is sort of,
Hmm?
Matan is a student of yours.
Also, Danielle, she's also a student. Okay, so first of all, the contribution of every ideal is of the what you expect is q to the n to the 1 minus the rank. So it's exactly the same thing when you replace I with a subgroup. There is a nice thing about what you get, what the leading term is, but we don't have a amount of time. So the leading term is like what is the we had before the number of divisors of D. Now it's the number of divisors of some polynomial in over the field, but okay.
But you saw, I thought this thing here, this x, y, x inverse minus 2a, that would have contribution, which is
This one?
zero, no, the first one. No,
This one? Yeah, this will go to 0.
But it's rank 1, no?
Sorry. Yeah, you're right. I should have this. Yeah. Now it's, yeah, thank you. Yeah. I should always add this because I have it in the back. I mean, it's like I assume it here, but
Okay.
yeah. Okay, so but the really interesting part is now we can define what we had before permittivity rank. We can define the Q permittivity rank. And this is very similar to what we had before. So we look at all the ideals that contain my word, W minus one. But and now I know that I want W minus one is not a basis element of I. Okay, this is actually not the precise thing, but okay, I plan to ask you why this is not this can be the right definition. And I just I mean, we don't have time. So the answer is that I mean A itself is always of rank one. So in this case, must exclude the case that I is A because A is always of rank one, and then we get something trivial. And this inequality makes us is the reason why we cannot generalize it completely the thing from before. Anyway, so I just tried.
You also need the other constraint you had before
Hmm?
that is generated along that. You also need the other constraint.
No, not anymore, because now I can show that everything, also with the groups that we didn't have it. I mean, if you have such thing, such critical ideal, it will be generated on back. You can show that every ideal that is important in the story will be generated on the back. Okay, so the conjecture is that the expected number of fixed points is up to -2 this time is of order and what we are able to prove is that this is true for these values of Q. I mean, the most interesting part here is 2 is I mean, really, and this is really the hard part. So we, in a sense, we know to control the. We know exactly what happens in this expression 1 over Q to the end. We don't yet prove it for the next one. Yeah. So yeah, I'm going to finish here. There are many.
Just like a notation, it's not Sn, it's like just n and x. Expectation of Sn W.
Yeah. So thank you.
But why do you look at FP to the n of the projective space? You said somehow that the projective space was more natural for.
Yeah, I mean, everything works also with the projective space. I mean, this was a bit slightly cleaner. But I mean, you will not get a nice expression with terms of ideals. You will get some coefficients if you do it with the projective space. But yeah, you're right. It's still, and perhaps it's, yeah, there is a parallel word where you, instead of defining it like that, you define it in there's another definition which works better with a projective space. And so it's not clear what's the best one yet, or whether perhaps they're all equivalent in a sense. So there are many. Yeah, there are many still. This project, the more we work on it, we expose many more open questions than we solve them. So this is really became a very big project with many directions. But I only told you at the beginning. And here.
Doron, you study these word measures, so you get this collection of distributions on a finite group given by all possible words. Is a family of distributions has any structure, any closure properties, any?
So again, so you ask.
You have a family of distributions on a finite group indexed by words of the free group.
Yeah.
Do you have any properties of this collection, any closure properties, anything to say about this family?
So there are, first of all, if you fix the finite group, you have only finitely many measures, finitely many distributions, by at least words in F2. I mean, if you fix the free group and you fix the finite group, you get only finitely many. There is some, I mean, I think if you look at, if the group is simple, then I think Lubotsky has nice results, which describes precisely what are the possible distributions you can get. So really it's up to, no, it's which, no, sorry, this is probably which images you can get. Yeah, no, I don't, we know some stuff about it, but we don't know exactly. I think you can say what are the possible images you get, not what are the possible. Yeah, I need to, I don't remember exactly at the moment. We don't know, we don't have a very good answer.
Start with talking about expanders, about whether, and I don't see the connection at the end to the starting point.
I mean, the hope was that you can, if you have a trial graph, right? You look at you want to use the trace method, just count closed path of length. So we want to count. You have a big trial graph. You want to count how many closed paths of length 1,000 you have. So every closed path in the trial graph corresponds to some word of length 1,000, and every word, the number of closed paths that correspond to it is the expected number. Is the number of fixed points of these words on in this action precisely. So, this is how. Yeah, but basically, this is how, like, for example, non-results about what I told you that you can take at the beginning with 16 elements. This is how it's proven. So you do this kind of computation.
Using this technology or?
No, so you don't. I mean, they use. I mean, this is so. This is the result of Sean Eberhard and Giselnik, and they use only. They only needed the leading term. So basically, they didn't have all this rationality. Just understood the leading term of show that it is 2 in general or a bit more for powers.
What is the result you're talking about?
The random trial graph, let's say over GLN over F2, with 16 random generators, is a family of expanders.
Say something about the reason why this rank, or even you can say it in SN better. Why is that the first like non-trivial coefficient?
I mean, okay, I can say that. Okay, if you take a primitive word, so you can have a. I mean, I go with this example. I can write even a very long. Let's take this word. Now in SN, we know, and it's an easy exercise because this word is primitive. It is part of a basis. Again, if I take it together with this word, this is now a basis of F2. So we know in advance this gives you just one. The expected number of fixed points is 1. You get the same. You get uniform distribution. Now you see that somehow if you do the combinatorics, you get many graphs. You get many graphs and many contributions, and there is cancellations. And the point is that, I mean, what we show is that okay, other words are not primitive, but as long as we don't see that they are not primitive, we still get these cancellations. I mean, this is a magical cancellation. Why do you get this? You get a very complicated sum, but somehow
there's like a basis change where it's simple, right? So
yes,
in the wrong basis, you need to have all these cancellations.
yes, yes,
But then
and this cancellation. I
if you
mean,
don't see, that's kind of a more intriguing thing to say.
yeah, but this is basic. Yeah, I mean,
Also don't get a 16 generator thing.
Eberhard and I mean it's Eberhard and just
It's strange that they can only compute the leading
I'm not
order
sure
of these
about
things and get something about the gap in the spectrum, right? That doesn't seem like enough information.
they get a gap in the.
But just from computing the leading order contribution to this doesn't seem like enough information to must be additional information being used.
No, I don't think. I mean, this is I mean, they have a bigger. The paper is longer, but this result is quite short. Given. No, I can't remember correctly. I need to think about it perhaps again. It's been a while since I thought about this computation, but I don't think they use much more than. because there's one trick or something, but not much more.
Okay. All the other questions offline, thank you so much.